Hello again, this is Ben Zimmer from Enable Training and Consulting, bringing you the next installment of the LV Mastery Tip Jar. In this installment we're going to talk about the Advanced FRC Framework. In the last session we talked about the basic FRC framework. It's my recommendation that most teams use the Advanced framework. Despite the fact that it's a little bit more complicated, I think in the end it's going to prove a lot simpler to maintain larger, more robust code, and code which is going to be programmed by more than one programmer. So we're going to take some time and go through that today, give you a tour of the framework, how to make modifications so that the teleop mode does what you want it to, and also a very quick introduction on how to modify the autonomous mode in the Advanced framework. I also want to point out at this time, if you're still in the first few weeks of the 2009 kickoff, we're doing a giveaway where you have a chance to win one of 6 free training subscriptions to our full training package. This is the same training we offer to our industrial customers. And if you just follow the link above, if it's still in the first few weeks of competition, we're going to be giving away 2 of those subscriptions a week. So just follow the link as you see it above on the website. So let's begin at our familiar Getting Started LabVIEW screen. We're going to create a new serial robot project. We're going to give it an appropriate name. Let's call this the Advanced Demo. Of course, give it an IP address. And this time choose the Advanced Framework. When you do that, take a look at the preview screen here, which is showing you a preview of what the project is going to look like. This is the basic framework, and you see when you switch to the Advanced Framework that the hierarchy becomes much more complicated. So click Finish to go ahead and build that project. And now that it's come up, let's take a quick look at this hierarchy in a little bit more detail. Again, we have our Robot Main.vi sitting at the root of the hierarchy. And again, that's the VI that we're going to run to deploy on our robot. But this time we've got a couple subfolders. The first is called typedefs, and we're going to spend a fair bit of time talking about what typedefs are. But in a nutshell, a typedef is like a sub-VI, except it's a way to hold a data type. And in the team code section, we have a series of sub-VIs which have been pre-created for us, and that's the code that we're going to modify. So just like before, we have a framework which we don't need to make any major changes to, but the main difference between the basic and the advanced framework is that all of our code is going to be encapsulated in these team code sub-VIs. Let's drill into the robot main and take a bigger look at that. So again, show the block diagram. So we can see now in our Robot Main.vi, we've got some instructions in this green text box. Take a moment to read that. But in a nutshell, what it's saying is don't change anything except the blocks that look like this. So if we activate our context help, we see that this sub-VI is called begin.vi. And if we go back to our robot project screen, we see that begin.vi is sitting in our team code directory. And that's indeed the case for all of these sub-VIs that we see here. The begin, the teleop, the finish, the vision, the time task, and several others that we're going to see when we do a brief tour in a moment. So again, we shouldn't change anything here. We should only change code which sits at the root of our project or within the team code or within the typedefs directory. So remember that as a golden rule. If you're going to make a change to a library function or something else, you need to make sure that you make a copy of that VI and place it in your project, as opposed to modifying the library or the framework VIs. And remember, the main reason for that is if we ever got a software update from National Instruments, then it would wipe out any changes that reside in the LabVIEW library directory and potentially cause your robot program to break. Let's begin now where it seems natural to start, which is at the begin VI. If we activate our context help and we hover over that guy, we see that it's got 4 outputs. One is the match info, one is the robot data, one is the vision data, and one is periodic task data. And we see that each of those is being wired into a different location. So this guy here, which is the periodic task data, no big surprise, it goes into the periodic task VI. Same approach for the vision. For the vision processing VI, there's a specific wire which contains the vision data, which comes from the begin VI. So if you remember back to the basic framework where we had our joystick open, our motor open, in the last example we opened a reference to both a gyro and a servo. We did all those on the left hand side and then we wired them into our loop. It's a very similar situation here, except instead of doing it on the base of the Robot Main.vi itself, we're going to do that in the begin VI. Again, the 2 data structures coming out of the begin VI at the top here are match, info, and robot data, and those ones go into our while loop here. So the while loop is where our fundamental code resides. We have our teleop code sitting in here. There is the same block, or at least a very similar block to what we had before, which is determining robot mode, which is determining which of these cases runs. And if we pull down this case structure, we see that there's a variety of cases here. There's autonomous enabled, teleop enabled, autonomous disabled, timeout, and finish. We're going to go through a couple of those, but not all of those right now. So let's assume we're in teleop enabled mode. That means we're going to be running in this case, and it's going to be this sub-VI which is going to run. So let's open this guy up really quickly. And what we see here is a very similar set of code to what we had before. There's a joystick get, which is pulling out axis 1 and axis 2, feeding those into an arcade drive block, and there's a watchdog feed. This is the same behavior we saw in the basic framework, it just looks slightly different. One thing you'll notice is that there's only one piece of data coming into this sub-VI containing all of these references. Whereas before we had the joystick get and the arcade drive sitting right on the basic robot main. As a result, we could wire these reference wires directly in from the opens. But we have a problem here. The reason we can't do that now is because this is all in a sub-VI. So the open functions have already happened, but in a different location. So what's necessary to do here is to bundle all of that information together, all of those different device references for joysticks, robots, servos, gyros, anything else you might be using, to bundle that all together into one wire, and to send that wire around to all the relevant sub-VIs. And in fact, that's exactly what this wire is. If we turn on the context help and hover over it, we see that its data type is a cluster of 3 elements. It contains a watchdog device ref, a joystick device ref, and a robot drive device ref. And if we hover over this block here, for those of you who have been watching all of the videos that we've put out, you'll recognize this as an unbundle by name function. So just like this wire is a bundle of different types of data, you need a function to be able to pull the data you want out of that wire, and naturally that function is called unbundle. So this function here, which is available from the cluster class and variant subpalette, is called unbundle by name. And the way it works, it's an expandable function. So by clicking on the handle at the bottom, you can drag it down to have as many elements as you want. Just undo that. And if you click on each of those elements, you can select which element you want out of that cluster. So you see that the code that's been created here for us has been pre-built with the ability to extract the watchdog, the joystick, and the robot drive. So what we're going to see in a moment is how to modify this data type so that it has additional information. As I mentioned, we're going to add, just like we did before, the servo and the gyro, and we're going to be able to talk to it using this sub-VI. We'll come back to this VI in a minute. For now, let's just close it and take a look at the begin VI. So as I just mentioned, in order for us to work with all the devices we want on our robot, we need to open those references and place those references into that bundle. And it's in the begin.vi that we do that. So recall that when we took a quick look at the begin VI a few moments ago, we saw that there were 4 major data types that came out of it. The first was the match info. There was also vision data, robot data, and periodic task data. Here is where those data types are created, and here is where all the references are inserted into them. So let's take a closer look at the robot data here. This function block we see here is called the bundle by name, and it sits right alongside the unbundle by name in the cluster class and variant palette. And the purpose of the bundle by name function, not big surprise, is that it puts data into a cluster. It adds something by bundling it onto that wire. And what you can see here is that it's been pre-created in our example code to allow us to bundle the watchdog and the robot drive. Just like the unbundle by name, this is an expandable function, so you can stretch it up or down to access all the data that's available inside it. Another really important point to understand about the bundle by name function is that there are actually 3 sets of terminals. The terminals on the left, which feed data into a specific element within the cluster. There's the terminal on the far right, which is the output of the cluster. But there's also a middle terminal, which is a required input to the bundle by name function. The purpose of the middle terminal is to tell the bundle by name function 2 things. One is, what is the type of the cluster that's coming in?